All right, guys, welcome to Honors Chem. Today we are going to talk about equilibrium, chemical equilibrium. So we've talked about chemical equilibrium a little bit before, but not to that big of a depth. So we're going to go a little bit more in depth today, and we're going to revisit something that we did in acids and bases today. We're going to have some equilibrium stuff going on. So remember ice charts or rice charts? We're going to do some of those today again. So you're going to definitely want a calculator handy, okay? So here we go, chemical equilibrium. Now, if you remember, equilibrium means that not all chemical reactions proceed to completion. We don't use up all of our reactants, okay? Many reactions reach an equilibrium condition. In fact, most do. This means that the forward and the reverse reactions balance each other, right? Remember, equilibrium means that the rate of the forward reaction is equal to the rate of the reverse reaction. The rate both ways is the same. So that means that even though individual molecules are still reacting, the net change of that system is zero. That's what equilibrium means, okay? This does not mean that there are equal amounts of reactants and products, okay, once equilibrium has been established, okay? It simply means that the products are being formed at exactly the same rate as the reactants are being formed from the products, okay? Rates are the same. So let's consider this reaction. We have A going back and forth with B, okay? So if we start off with only A, so we're going to start off only with A. Notice at our beginning, we only have A, okay? As we use up A, B starts being made. So our concentration of A as we use it up is going to go down, and our concentration of B as we start making it is going to go up. Eventually, we will get to a spot in that reaction where the concentrations of A and B no longer change. So when we get to that, which is about here, where that concentration of A and B no longer change, it means that we have equilibrium. That's what's going on, okay? So notice that when equilibrium has been established, the concentration of the reactant and the product are no longer changing. This does not mean that the product has stopped forming. It simply means that the amount of the product that is being formed is now equal to the amount of product that is being converted back to the reactants. Okay? The rate of the forward reaction is equal to the rate of the reverse reaction. So equilibrium means that the rate of the forward is equal to the rate of the reverse. So when we reach equilibrium, we have the rate of the forward reaction is equal to the rate of the reverse reaction. That's what equilibrium means in a nutshell. Okay, so this is how we go about mathematically expressing equilibrium with concentrations, okay? Equilibrium expressions are a ratio that we use to describe the relationship between concentrations of product compared to the concentrations of the reactants once equilibrium is established. This ratio is called the equilibrium expression, okay? So here's our general reaction. If I have the lowercase letters are our coefficients, okay? So these are our coefficients. And the uppercase letters are the molecules or atoms, or they're the formula of what's being reacted, okay? So notice our equilibrium expression. When we do this, we have an equilibrium constant that this is a constant, okay? And we have our products over our reactants, okay? So notice that our A, because it's a reactant, is going to be here. And notice that our coefficient becomes an exponent. So coefficients become exponents. Okay? So coefficients become exponents, and our products are always on the top, our reactants are always on the bottom, and coefficients become exponents. Okay? And this is based off of our balanced chemical equation. Okay? So we should always say this. This is based on the balanced chemical equation. Okay, so let's think about this mathematically. If our equilibrium expression is larger than 1, doesn't it mean that we have more products than we have reactants? And if we have more products than we have reactants, that means that our products are favored at equilibrium. That means we will make more products. So this reaction may not go to completion, but we actually get pretty far along the way. Okay? If our equilibrium constant is less than 1, that means we don't make very many products. That means our ratio of products over reactants is very small. That means we have more reactants than we have products. So reactants are favored at that equilibrium. So we really don't get very far in making our products for that kind of a reaction. Okay, so I want you to think about this. If I wanted to draw a graph of concentration, so we're going to put concentration on the y-axis, and we're going to put time on the x-axis for A going back and forth with B for a KQ that is greater than 10. That means we have a lot of products. So how would that work? Take a minute and draw that. Okay, I'm going to draw it and see if you compare yours and see if it is like mine. So if my equilibrium constant is greater than 10, which means I have a lot of products, my concentration of A is going to start out really high. My concentration of B is going to start out really low. But if I make a lot of products, my concentration of A is going to go down really, really quickly. Well, and my concentration of B is going to go up pretty quickly. So B is going to end up with a greater concentration than A when we're done. Okay, let's look at scenario B, where our equilibrium constant is less than 0.1, which means we're going to have a lot of reactants, not a lot of products. So draw your curve, take a minute, and see if you can compare. So I'm going to put B here, and if my equilibrium constant is less than 0.1. How do you draw it? A is going to start out here, as always. B is going to start out here. But I'm not going to make very many products. It's just going to go down just a little bit, and B is going to go up just a little bit. Notice I have equilibrium happening in both graphs, but the concentration of the products is vastly different depending on how big my equilibrium constant is. Okay? All right, so here we go. Equilibrium's expressions are always true for a given temperature. Now, I want to reinforce that really quickly. So let's highlight that. Equilibrium expression is always true for a given temperature. So if I change the temperature of that reaction, that equilibrium constant is going to be different. They're temperature specific. Okay? In fact, a change in temperature is the only thing that mathematically will change that equilibrium constant. Okay? It is important to note that the species shown in the equilibrium expressions are expressed in terms of molarity. Okay? So once again, we are going to be doing molarity, which is our big capital M, which is moles per liter. So we have to look at concentrations, and we can only express things in the equilibrium constant or expression that can be expressed in concentrations. Okay, so solids and liquids, because they can't be expressed in molarity, are never part of the equilibrium expression. And I will highlight that. That is super, super important. Solids and liquids are never part of that equilibrium expression. Only gases and aqueous, well, not aqueous solutions, but solutions that are dissolved in a solution, okay? Because their amounts cannot be expressed, solids and liquids cannot be expressed in terms of molarity, okay? They are not homogeneously dispersed in the reaction vessel. However, gases, ions, or molecules in solutions can be expressed in terms of molarity. These are the only species shown in an equilibrium expression, okay? Try and remember that. Okay, do your best to remember that. Okay, so we're going to write the equilibrium expression here. Now remember, when we write equilibrium expressions, we have our products to the exponent that the coefficient is over our reactants to the exponent that they have, okay? So let's write our equilibrium expression for nitrogen bonding with hydrogen to make ammonia, otherwise known as the Haber process. Okay, this is how we make ammonia to make fertilizer. All right, so the Haber process. If I look at my products, I have ammonia and I have a coefficient of 2. So my equilibrium constant expression is going to have my concentration of ammonia on top with a square, because that square comes from that coefficient of 2. And on the bottom, I have my reactants of nitrogen, and it doesn't have a coefficient. I can, of course, put a coefficient of 1 there if I want, but it's implied, so I can just not put that 1 there either. And I have my concentration of hydrogen gas, and I have a coefficient of 3 here, so I need to put a 3 there. Okay? So that would be my equilibrium expression for the Haber process, making ammonia. I want you to take a minute and write the equilibrium expression for carbon bonding with oxygen to make carbon monoxide. Take a minute and write that down. Okay, do you have it? Now, this is what you should have. Our product, we have carbon monoxide. And we have 2 of them, so it should be squared. On the bottom, we should have our reactants. Oxygen, there's no coefficient. And get this, I'm not putting in carbon. Why? Why did I not put carbon in the equilibrium expression? Do you see this? Let's highlight this really quick. It's a solid. I cannot put solids in the equilibrium expression. No solids, no liquids, only gases or things that are dissolved in solution. Okay? So my equilibrium expression for carbon monoxide being formed is actually just my ratio of carbon monoxide squared over oxygen. That's it, because I can't put carbon in there. Okay? You guys good with that? All right. Number 4, example 4, write the chemical equation that has the equilibrium constant for this expression. So can you do the reverse? Remember, products are on the top. So what are our products? We have carbon monoxide and oxygen. And what does that square from that carbon monoxide tell us? It tells us our coefficient. So let's see if we can deconstruct this. Okay? So I would have 2 carbon monoxides, right? Because that 2 is going to become a coefficient, plus oxygen is going to go make me 2 carbon dioxides, right? Because no, did I have it reversed? I did. Silly me. That's really, sometimes I make mistakes on purpose. Do you know that? Okay, so really our products need to be carbon monoxide. Okay, so we really should have carbon dioxide, 2 of them going to carbon monoxide, 2 of them plus oxygen. This is our equation. Remember, products are on top and reactants are on the bottom. Now it's kind of hard because we always want to put the top first and the bottom second. It's reverse. Products are on top. The reactants are on the bottom. Okay? All right. So here we go. For a given reaction at a given temperature, the equilibrium constant will always be the same, regardless of the initial concentrations of the reactants and the products. To test this statement, 3 experiments were carried out using the following reaction. So we have hydrogen plus iodine giving us 2 hydrogen iodides, equilibrium. So let's look at trial 1. We start out with just hydrogen and iodine. We start out with no hydrogen iodide. We let it get to equilibrium, we have our concentrations. Okay? Our equilibrium constant expression would be 2 hydrogen iodide squared over hydrogen and iodide. Do you guys agree with that? Okay, take a minute, make sure that looks right. Okay, so we take our equilibrium concentrations and plug them into this expression, and we get an equilibrium constant of 49.70. Okay? So let's look at experiment 2. We start off this time with 0 hydrogen and iodide, just hydrogen iodide. So it's going to decompose into hydrogen and iodine. We let it get to our equilibrium and we plug in the values. Mathematically, we still come up with the same constant. And then here we start off with 1 mole of each in per liter. We let it get to equilibrium, and once again, we come up with the same equilibrium constant. So notice that it doesn't matter where the equilibrium starts from, our initial concentrations. Once we reach equilibrium, we will always get the same equilibrium constant. That's why it's called a constant, because it doesn't change. Okay? Now, this means that we are doing, do you see this? We're doing initial concentrations and then equilibrium concentrations. Does that ring a bell from when we did weak acids and weak bases and we did ice charts? Yes, ice charts are coming at you again. Okay, so here we go. Note that the equilibrium concentrations are not the same in all 3 trials. Yet when each set of equilibrium concentrations is put in the equilibrium constant expression, the same equilibrium constant is received at each time. I can't even think of the right word, is calculated. Each set of equilibrium concentrations represents an equilibrium position. Okay? So here we go. Example. You are definitely going to want a calculator from these. For the reaction at a different temperature from the above example, we had the same reaction, hydrogen plus iodine going back and forth with 2 hydrogen iodides. when 1 mole of hydrogen and 1 mole of iodide are placed in a 1 liter container. How convenient, 1 mole per liter, 1 molar, right? And allowed to come to equilibrium, there are 0.2 moles of both hydrogen and iodine remaining. The rest has been converted to hydrogen iodide. Find the value of the equilibrium constant at this new temperature. Okay, so here we go. Ice charts. So we want to put our reaction at the top, just like we used to. So we have hydrogen plus iodide going back and forth to hydrogen iodide 2. Okay, so there's our reaction, our initial concentration. Now remember, these concentrations all need to be molar, which means that they need to be mole per liter. So my hydrogen, let's look at this. I have 1 mole in a liter, right? They're placed into 1 liter. So 1 mole per liter gives me a 1 molar concentration. And iodide, I also have 1 mole in a liter. So 1 mole in a liter is a 1 molar concentration, and I have 0 hydrogen iodide at the beginning. Okay, change. Here's my change. So I know that these go down, right? I am given my equilibrium concentration. So my equilibrium concentration is 0.2 moles in that 1 liter container. So I know it's 0.2 molar. So how much did I lose? What's the difference between 0.2 and 1? Isn't it 0.8? So that means that my change here was negative 0.8. Do you guys agree with that? Okay, and now if you notice, for each one of these hydrogens, I make 2 hydrogen iodides. So if I lost 0.8, wouldn't I make, what's 0.8 times 2? It's 1.6. So wouldn't I make 1.6 moles? And it's still in that 1 liter vessel, 1.6 moles. So my equilibrium constant or concentration of hydrogen iodide would be 1.6 moles per liter. Do you guys agree with that so far? Okay, so there's my ice chart. Let's write out our equilibrium constant expression. I'm going to change colors here. So my equilibrium constant, remember products on the top. So I have hydrogen iodide, and I have a coefficient here of 2. So I need to square this all over hydrogen and my concentration of iodine. And this is my equilibrium concentrations. So I'm going to put in my equilibrium concentrations. So I'm going to have 1.60 squared all over 0.20, right? This goes up here, this goes here, and this goes here, 0.20, okay? So when I do that, let's see, 1.6 squared divided by 0.2 squared gives me an equilibrium constant of 64. Now notice we have no units because this is molar squared, molar times molar, which is molar squared. So equilibrium constants are usually unitless. They are just numbers. Okay? All right, let's do our next example. At a certain temperature, our equilibrium constant for 10.5 for the carbon monoxide plus hydrogen going to methane. No, this is methanol. calculate the following concentrations. So I have carbon monoxide in an equilibrium containing 0.933 moles per liter hydrogen and 1.32 moles per liter of methanol. Okay, so let's write out our equilibrium expression here. So our equilibrium expression for this reaction, let's put this here. If I can get this to line up. So I want my equilibrium expression. Remember, products are on top, so I'm going to put methanol on top because it's gas. We can use that. Carbon monoxide on the bottom, gas, and hydrogen. Oops, not iodine, hydrogen. Now, hydrogen needs to be squared because there is a coefficient of 2 there. Okay? How do you feel about that? Is that what you agreed? Okay, so we're gonna solve for, let's see, in A, we want to solve for carbon monoxide, right? So if I solve for carbon monoxide, isn't carbon monoxide going to be equal to our methanol concentration divided by our equilibrium constant multiplied by our hydrogen concentration squared? Do you guys agree with that setup? Okay, so we're going to plug in our methanol concentration. So I'm going to have 1.32 molar divided by our equilibrium constant, which is 10.5. And our hydrogen ion, or our hydrogen concentration, is 0.933 squared. Okay? All right, so we're going to do the math here. So 1.32 divided by 10.5, also divided by 0.933 squared. Okay, so how many sig figs do I have? It looks like I have 3. So for 3 sig figs, this would give me 0.144. And I'm looking for a concentration, so this would be moles per liter. Okay, how'd you do on that one? Okay, let's do B really quick. So I want to look for hydrogen. So hydrogen, my concentration of hydrogen is squared. So it would be the square root of this whole thing. So it would be the square root of my methanol concentration divided by my equilibrium constant and divided by my carbon monoxide concentration. So I'm going to plug those in. So I need to take the square root of, let's see, 0.325 for my methanol concentration, divided by 10.5 for my KEQ, and divided by 1.09 for my carbon monoxide. Okay, so if I do that, so I'm going to take the square root. So I'm going to actually take 0.325 divided by 10.5 divided by 1.09, get that number, and then I'm going to square root that. So when I do that, I have 3 sig figs. That gives me 0.169 moles per liter of hydrogen. Okay, and then C, methanol. So I want to solve for methanol. So methanol, CH3OH, is going to be equal to my equilibrium constant multiplied by my carbon monoxide concentration multiplied by my hydrogen ion concentration squared. Okay? So I have my equilibrium constant, which is 10.5. My carbon monoxide concentration is 3.85. And my hydrogen concentration is 0.0661, and I need to square that. Okay, so when I do that to 3 sig figs, so 10.5 times 3.85 times 0.0661 squared, 3 sig figs, 0.177 molar. So 0.177 molar methanol. Okay, so it ends up just being a bunch of math. Okay, I think this is our last example here. Yep. So for the reaction, we've got carbon dioxide, water, and hydrogen, and carbon dioxide. Everything's gas, so everything's going to show up in this equilibrium constant. The value for the equilibrium constant is 0.227. If I have 0.1 mole of carbon monoxide and 0.1 mole of water are placed in a 1 liter container, determine the concentration of all species once the equilibrium is established. Okay, this is another ice chart. So first thing first, let's make our ice chart. So let's start with that reaction. We have carbon monoxide plus water going back and forth to hydrogen and carbon dioxide. Okay. Now we need to find our initial concentrations. So it says I have carbon monoxide, I have 0.1 mole in 1 liter. So that's going to give me 0.1 mole. And same with water. I have 0.1 mole of water. I should write mole here in 1 liter in a 1 liter container. So that gives me 0.1 molar there. I'm going to have none of this to begin with. Okay? I just totally messed up. So this is going to kind of get in the way. So I'm going to get rid of this. But just know that we always have to get our concentration in molarity. So 0.1 in 1 liter. Okay? So our change. So we know with equilibrium, we've got to make some products, right? It's got to move to some products. So we know that this is going to be negative X. And for each carbon monoxide that we use up, we also use up 1 water. And for each carbon monoxide and water that we use up, we make 1 hydrogen and we make 1 carbon dioxide. So this is going to be positive X. This is going to be positive X. Be aware of your stoichiometry here. Make sure that those coefficients match up with the variables that you're putting in your ice chart. Okay? So our equilibrium line, we are going to have 0.1 minus X and 0.1 minus X and X and X. Okay? So let's make our equilibrium expression here. So equilibrium expression, we have our products on top, we have hydrogen and carbon dioxide, and we don't have to really worry about exponents because we have no coefficients here. Carbon monoxide and water. Okay, so we're going to start plugging in values. So my equilibrium constant is 0.227. My concentration of hydrogen is 0.1 minus X. And my concentration of carbon dioxide is 0.1 minus X. And my concentration of carbon monoxide is X, and my concentration of carbon dioxide is also X. So I'm going to simplify that a little bit to 0.227 equals 0.1 minus X squared all over X squared. So this is a perfect square, so I can square root this. So if I square root both sides, I can get this. So I'm going to take 0.277 and square root this. 0.277, or sorry, not 277, 0.227. So I get 0.476, and I'm going to give it one more digit because I just don't want to have rounding errors, is equal to 0.1 minus X all over X, right? So now I just solve for X. So I'm going to have 0.4764X is equal to 0.1 minus X. So I'm going to add that X to both sides. So this is going to be 1.4764X is equal to 0.1. Okay, so I'm going to take 0.1 now and divide it by 1.47. So 0.1 divided by 1.4764 will give me an X value What did I do wrong here? Okay. 0.4. Oh, never mind. I just totally set that up. Totally upside down. Oh boy. Never mind, guys. I'm sure you guys saw that. I totally set that up upside down. Okay, let's redo this. It is definitely a Friday afternoon and I am tired, and I can tell. Okay, let's start that over. I am so sorry. Okay, so let's start this over. So products on the top. So this is going to be 0.227 is equal to X squared over 0.1 minus X quantity squared. That's where my mistake was. I put the wrong variables in the wrong place. So we're going to take the square root of both sides, okay, and we get 0.4, it's not writing, 0.4764 is equal to X minus, or over 0.1 minus x. Okay, so we're going to get 0.04764 minus 0.4764x is equal to x. There's my mistake. And then we're going to have 0.04764 is equal to 1.4764x. Okay. And then if we do that, we get x is equal to 0.0323. So this is going to be 0.0323, 0.0323. Okay, so if I do 0.1 minus x, that gives me 0.97 with my sig 0.097 with my sig figs. Okay, so this is my concentration of carbon monoxide, my concentration of water, and my concentration of hydrogen, and my concentration of carbon dioxide. Okay, I am sorry. That is how you do the math. Make sure you keep the products on the top and the reactants on the bottom. All right, have a great day. We'll see you later. Bye.